Welcome back to The Explainer. Today, we're diving into something that looks, well, pretty simple, but it does something absolutely incredible. It can take a single beam of light and reveal all the hidden colors tucked away inside. It's called a diffraction grating, and believe me, it helps us unlock some of the biggest secrets in the universe.
Okay, let's kick things off with a question that kind of messes with something we all learned in science class. You know how they say light always travels in a straight line? Well, what if it doesn't? What if I told you that under just the right conditions, light can actually bend and spread out and create these amazing, detailed patterns all by itself?
So here's our game plan for this explainer. First, we're going to look at this weird little detour light takes. Then, we'll see how to crank that effect up to 11. We'll get into the nitty-gritty of how it works, the wave physics behind it all, and finally, we'll see how to use all this to measure the true color of light itself. Sound good? Let's go.
All right, first up, we need to understand this curious detour that light can take. This whole idea has a name, and it's called diffraction. And look, it's not just for light, it happens with any kind of wave. Think about sound waves coming through a doorway, or water waves passing through a small gap in a barrier. They don't just go straight through, right? They spread out, and that's exactly what light does too.
So let's picture this. You take a laser and shine it through one tiny little slit. Now, you'd probably expect to see just a single sharp dot on the wall behind it. But that's not what happens. Instead, you get this weird fuzzy pattern. There's a big bright blob in the middle, and then these fainter, dimmer bands off to the sides. It's bizarre. And this effect, it has a name. Fraunhofer diffraction.
Okay, that pattern is kind of cool, but honestly, it's way too blurry to be useful for any real measurements. So, what's the solution? How do we make it sharper? Well, what if instead of just one slit, we used a whole bunch of them?
And bam! That brings us to the star of the show, the diffraction grating. It's really just a piece of material that's covered in thousands, sometimes tens of thousands, of perfectly parallel, perfectly spaced little grooves or slits. So yeah, we're not just talking a few slits, we're going from one slit to n slits, where n is a huge number. And the result? Whoa, it's night and day. On the left, you've got that blurry mess from the single slit, but on the right, when you use a grating, the whole pattern snaps into focus. You get these incredibly sharp, super distinct, bright little lines. And that is something you can measure with real precision.
Okay, so the big question is, why? Why does adding more slits make everything so sharp? The answer, and this is the core of it all, is a concept called wave interference. Okay, let's break down how one of those bright spots actually gets made. Picture the light waves coming out of every single one of those thousands of slits. They all start out perfectly in sync, like soldiers marching together. But to get to a screen on the other side, some have to travel a little farther than others. Now here's the magic. At very specific angles, the distance is just right so that the peak of a wave from one slit lines up perfectly with the peak from the next slit and the next and the next. They all add up, they build on each other, creating this super bright spot. That's what we call constructive interference. So, what about all the other angles? Well, at those spots, the exact opposite happens. The peak of a wave from one slit arrives just as the trough, the low point, of another wave shows up. And what happens when a peak meets a trough? They cancel each other out. Poof! Nothing. Darkness. That's destructive interference. And it's the reason we see those clean black spaces in between the bright lines.
Okay, so we've got this awesome tool that makes super sharp patterns of light. Cool, but so what? What's the point of all this? Well, this is where it all comes together. This is the payoff, because now we can actually measure the true nature of color itself.
Believe it or not, the entire relationship between the grating we're using, the light we're shining, and the pattern we see, it all boils down to this one beautiful, simple formula. This is the grating equation.
Let's just take a quick look at what's in here. D is just the spacing between the slits on our grating. That's a fixed number we already know. Theta is the angle we see a bright spot at. That's the part we can actually measure with a protractor or a sensor. M is just a simple counter. Are we looking at the first bright spot, the second, the third? And lambda, that's the big one. That's the wavelengths of the light. It's the physical property that our eyes interpret as color. So here's the absolute crucial point. Since we already know D, the slit spacing, all we have to do is measure the angle, theta, where we see a bright spot. And once we do that, we can use this simple equation to calculate lambda, the light's exact wavelength.
We are literally turning a simple measurement of an angle into a fundamental property of light itself. How cool is that?
And you can see how this plays out in the real world. Take a look. For a red laser, which has a longer wavelength, the light gets bent at a pretty wide angle, almost 24 degrees here. But look at green or blue. Their wavelengths are shorter, so their angles are smaller. So you see, just by measuring that angle, we can figure out the exact wavelength and therefore the precise color of the light we're looking at.
So let's wrap this up. What have we learned? Diffraction gratings are amazing because they can split a beam of light into its component colors. They do this using the physics of wave interference to create these super sharp, easy-to-measure patterns. And the real kicker is the grating equation, which gives us the power to turn that pattern into a hard number, the light's actual wavelength. It's the ultimate example of turning a simple visual effect into a seriously powerful scientific instrument.
And this isn't just a cool lab trick. This is where it gets mind-blowing. Astronomers point their telescopes at stars light years away, pass that starlight through diffraction grating, and just by looking at the resulting pattern, they can tell you exactly what that star is made of. It's incredible. So it really makes you think, doesn't it? If a simple piece of glass with some scratches on it can reveal the chemical secrets of a distant star, what else are we missing? Right here, just by looking with our own eyes.